Dear students, Assalamu alaikum. Welcome to this channel. Students, in the previous lecture, we used Coulomb's law to find the electric field intensity due to a point charge. And this was the result. That is, E is equal to 1 over 4 pi epsilon naught Q over R square. And as you know that electric field is a vector quantity, so vectorially it becomes this. And it came from this situation. If we have a point charge and if we want to find the electric field intensity due to this point charge at a distance r from it, we place a test charge there and the electric field intensity at this position was found to be this. Now, suppose if we have a distribution of charge in some region of space. For example, if we have some charges, suppose there are certain charges in this region. Let me call this charge as Q1 and this charge is Q2 and this charge is Q3 and this charge is Q4. Suppose we have 4 point charges in this region. So can we find the electric field intensity due to all these charges, suppose at this point? Yes, we can. But how? How can we find this electric field intensity? Again, by using Coulomb's law. Okay, if we use Coulomb's law to find the electric field intensity due to this distribution of charge at this point, then the result would be this. If this Q1 is at a distance R1 from this point, then the electric field at this point is supposed in this direction. This is due to the charge Q1. This is electric field E1, this is point charge Q1. And suppose if this charge Q2 is at a distance R2 from this point, then the electric field due to this point charge Q2 would be, suppose, in this direction and of certain magnitude. Now, if we consider charge Q3, suppose this charge Q3 is negative, and if it is negative, then what will be the direction of the electric field? Yes, opposite to this. And again, the direction of electric field is in the direction of force, but this time the force is force of attraction. If I consider all those charges to be positive, and suppose if the distance of that point from this charge is R3, then the electric field due to this point charge Q3 at this point, suppose, will be in this direction. And let me represent this by E3. And again, due to this charge Q4, let's suppose charge Q4 is here at this point, just to clarify it. If this charge Q4 is here, and then suppose the distance of the charge Q4 from that point is R4, and the electric field due to this point charge will be, suppose, in this direction. Let's suppose this is E4. So we are using Coulomb's law to find the electric field intensity due to this distribution of charge at this point. Now, next is, now we are supposed to find out the resultant electric field at this point due to this whole distribution of charge. For that, what do? We use the principle of superposition. We add all the electric fields vectorially at this point. So I suppose the resultant electric field is E, and this is the vector sum of E1 plus E2 plus E3 and as E4. We have taken the vector sum of all those electric fields at that point. So we have found the electric field at this point. This is the resultant electric field at this point, which we have found by using Coulomb's law. But you see, it became very tedious. It becomes very difficult to find out the electric field intensity using Coulomb's law. So there must be an alternative to this solution. So the alternative to this Coulomb's law is another law called Gauss's law. Gauss's law is again, you can say that Gauss's law is equivalent to Coulomb's law. Coulomb's law develops a relationship between the charge and the electric field set up by that charge. Again, the Gauss's law also develops a relationship between the charge or charges and the electric field set up due to that distribution of charge. Here we have the distribution of charge, and here we have the electric field intensity due to this distribution of charge at this point, which we have found by Coulomb's law. But to be very simple, we use another law, and that law is called Gauss's law, and that is also developing a relation between the charge and the electric field. So we can say that it is equivalent to Coulomb's law. So Gauss was a German mathematician and astronomer. As he was a mathematician, so he gave a theoretical law to solve this situation. He gave a theoretical law to solve the electric field intensity due to distribution of the charge. Okay, now next, if we want to find the electric field intensity due to this distribution of charge, we are going to use Gauss's law. And first of all, we state this Gauss's law, and then we'll derive the formula for that. Okay, first of all, let me state this Gauss's law. And this Gauss's law, again, I'm telling you, it develops a relationship between the charge and the electric field setup due to that charge. So Gauss's law, according to the statement of this Gauss's law, this is the statement of Gauss's law. The statement is the electric flux to a closed surface is equal to 1 over epsilon naught times the total charge enclosed by that surface or by A. So to derive this Gauss's law, we assume a point charge which is enclosed by a surface, a spherical surface, which is in fact our closed surface of radius r. This is our closed surface, which is in the form of a sphere, and it is having radius r. Suppose a point charge is placed at the center of this closed surface. Now we are supposed to find out the electric flux due to this point charge to this whole surface, which is our closed surface in the form of a sphere. Now to find the electric flux to this whole surface, first of all, we have to divide this whole surface in the form of small patches. The question is why? Why we are going to do this? Because to describe a surface and its orientation, we require an area vector. Area vector, if I just describe this area vector, and you all know that area is a scalar quantity, yes, but sometimes in certain situations we require the orientation of that surface, of that area, and that becomes very important in case of electric flux. So if I suppose here a surface, let's suppose this is a surface whose area is, suppose I represent its area by A, this is the magnitude of this surface. Now how can I describe the orientation of this surface? So to describe the orientation, I'll draw a vector normal to this. And this normal vector is representing the area vector. And you know that any vector is, in fact, that can be written as the magnitude of that vector and into the unit vector. So this A is representing the magnitude of the surface, and this n unit vector is representing the direction, the orientation of this surface. So this is an area vector. Now in our given situation, a single area vector would not be sufficient to describe this whole spherical surface because it is curved. At every position you have different direction of the area vector. So that's why we have to divide this whole surface in the form of patches. And these patches should be very, very small so that they become flat, like this. And then suppose here we have some patches, we divide this whole surface. Now we represent these patches with the area vectors. Let's suppose this patch is flat and its area vector is in this direction. Let me represent this area vector by delta A1, and suppose as we have divided this into n patches, so we have n area vectors to represent these patches, their orientation. Field due to a point charge is always radially outward. So for this point charge, we have the electric fields, electric field lines. Suppose this is the electric field in this direction passing to this area. Let's suppose this electric field is E1 and another one, we have n electric field lines. These are passing through these patches. Now we find out the electric flux through every patch, and you can see the angle between the electric field and the area vector, and using the definition of electric flux we find out electric flux through area delta A1, we have just written the magnitude of that, is equal to flux represented by phi, and this is phi 1, and here the flux passing to this is the dot product of the electric field in the area vector, so this is E1 dot delta A1. So you can see the angle between this electric field and the area vector as they are parallel, so the angle becomes 0. So we write E1 delta A1 cosine of 0 degree, and cosine of 0 is 1, so E1 delta A1 into 1, so E1 delta A1. As the condition is same for every patch, so we can write similarly for every on electric flux through our nth patch delta AN is equal to phi n is equal to En delta AN. So these are the electric flux through every patch. Now as we are supposed to find out the electric flux to the whole surface, so for that we add them up. So we write the other result, electric flux through the whole surface. This is the total electric flux. So if I represent this by phi, then this is equal to phi 1 plus phi 2 plus phi 3 plus so on up to phi n. Add them up. Phi is equal to phi 1 is E1 delta A1 is now the electric flux to the whole surface. So phi is equal to, now just look at this equation. Let me call this as equation 1. Okay, you see, as every patch is on this surface of this sphere, and every patch is at the same distance because the charge is placed right at the center of this sphere. So every patch is at the same distance, that is equal to the radius of the sphere from this point charge. And so electric field for every patch will be the same. And so we can write E1 is equal to E2 is equal to E3 and so on is equal to En, and let's suppose this is equal to E. So on every patch electric field is same. So then equation 1 becomes phi is equal to, replacing E1 with E, replacing E2 with E, replacing E3 with E. So this becomes E delta A1. So taking E as common, phi is equal to E into delta A1 plus delta A2 plus delta A3 plus so on up to delta AN. Now the electric field due to this point charge Q at a distance R is given by this E is equal to 1 over 4 pi epsilon naught Q over R square. So we can replace this E by its formula. We can write phi is equal to 1 over 4 pi epsilon naught Q over R square. Then within the bracket. So students, can you tell me what is there within the bracket? What is this? Delta A1 plus delta A2 plus delta A2 so on up to delta AN. This is in fact the whole surface area of this sphere. So I write this as surface area of the sphere, which is our closed surface in this case. So that is equal to phi is equal to 1 over 4 pi epsilon naught Q over R square, and the formula for the surface area of a sphere is 4 pi R square, and solving this, R square and R square cancels out, 4 pi and 4 pi cancels out, so the result becomes phi is equal to Q over epsilon naught. So students, this is the electric flux due to a point charge which was enclosed in a sphere, which was a closed surface. Now students, you see, just look at this formula. And a very important thing, a very important result we are extracting out of that formula is that the electric flux through a closed surface is independent of the shape of closed surface. This is very, very important sentence. Remember that electric flux through a closed surface that is independent of the shape. Electric flux to a closed surface is independent of the shape. Remember that if it is an open surface, then electric flux depends upon the shape of the open surface. But in case of closed surface, electric flux does not depend upon the shape of the closed surface. So from this formula, we see that electric flux through a closed surface depends upon the amount of the charge enclosed by that surface and the medium inside that closed surface, that is epsilon naught in this case. So this is the result for the electric flux due to a point charge through a closed surface. Now, if we have a distribution of charge in certain region of space, again, let's suppose we have charge Q1, Q2, Q3, so on, up to Qn charges are there in this region of space. And we are supposed to find out the flux due to all these point charges, and definitely we are supposed to find out the electric field due to all these point charges as described earlier. So for that, first of all, as we know that electric flux due to a point charge is independent of the shape of closed surface. So this time we enclose all these charges in a closed surface of which shape? Of any shape, of arbitrary shape. So whatever is the shape of the closed surface, let's suppose this is the shape of our closed surface, because electric flux is independent of the shape of the closed surface. So using this relation, phi is equal to Q over epsilon naught, we can find out the electric flux due to each point charge, and then we'll sum it up to find the total electric flux due to all those point charges. Okay, we proceed. Now, electric flux due to Q1 through the surface is equal to, let me call this as phi 1 again, and this is Q1 over epsilon naught. We have used the previous formula for that. Again, similarly, now again the total electric flux. So the total electric flux is the sum of all. So phi is equal to phi 1 plus phi 2 plus phi 3 plus so on up to phi n. So phi, so we can take 1 over epsilon naught as common, 1 over epsilon naught, so Q1 plus Q2 plus Q3 plus so on up to Qn. So students, what is this within the bracket? This is the total charge enclosed in that surface. So from this, phi is equal to 1 over epsilon naught into this Q1 plus Q2 plus Q3 plus Qn. This is the total charge enclosed by that surface. And this is the mathematical form of Gauss's law. So students, we have derived the Gauss's law, and we'll be using this Gauss's law to find the electric field intensity due to some distribution of charge, and this would become very simple for us to find the electric flux, and then if we can find the electric flux, then we can find the electric field as well by using Gauss's law. Thank you.